Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A few weeks ago, machine learning and AI researchers, practitioners, and students from Africa and around the world met in Cape Town for the second annual Deep Learning Indaba, an event that aims to expand African participation and contribution in the field. While I wasn't able to make it to Cape Town myself, I did have a chance to speak with some of the event's awesome speakers, and I'm excited to present to you our Deep Learning Indaba series. In this, the first episode of the series, we're joined by Sara Hooker, AI resident at Google Brain. I had the pleasure of speaking with Sara in the run-up to the Indaba about her work on interpretability and deep neural networks. We discuss what interpretability means and when it's important, and explore some nuances like the distinction between interpreting model decisions versus model function. We also dig into her paper Evaluating Feature Importance Estimates and look at the relationship between this work and interpretability approaches like LIME. We also talk a bit about Google, in particular the relationship between Brain and the rest of the Google AI landscape, and the significance of the recently announced Google AI Lab in Accra, Ghana, being led by friend of the show Moustapha Cisse. And of course, we chat a bit about the Indaba as well. Before we jump in, I'd like to send a big shout out to our friends at Google AI for their support of the podcast and their sponsorship of this series. In this podcast, you heard Sara talk about the AI residency program she's in at Google. Well, just yesterday, they opened up applications for the 2019 program. The Google AI residency is a one-year machine learning research training program with the goal of helping individuals become successful machine learning researchers. The program seeks residents from a very diverse set of educational and professional backgrounds from all over the world. So if you think this is something that sounds interesting, you should definitely apply. Find out more about the program at g.co/AI residency. And now, on to the show. All right, everyone, I am on the line with Sara Hooker. Sara is an AI resident at Google Brain. Sara, welcome to This Week in Machine Learning and AI.
Hi, Sam.
I am so excited for this conversation. Let's start with a little bit of background. And you've got a somewhat non-traditional background for a Google Brain researcher. You taught yourself machine learning. Tell me a little bit about that.
Yeah, it's interesting with these type of questions of how did you get into research. Often you have these very common reference points that are shared. I went to this school and then I did this PhD, and a lot of my career has been driven by things which are less compactly described, which is they've been very much driven by curiosity and like moderate obsession with certain questions. But I think probably one of the pivotal moments was I started a nonprofit 4 years ago. And it was Cool Delta. Well, it is Cool Delta Analytics, and it works with other nonprofits all over the world, and also teaches machine learning. But at the time when I started it, it was my background originally academically is in economics, and I was very excited to just do economic modeling for nonprofits. And then the composition of volunteers that we had, because we were in the Bay Area, was this kind of eclectic mix of economists and engineers and machine learning researchers. And that was kind of the turning point for me, because in some ways the tasks that we were looking at were really exciting. We were working with nonprofits that were doing education programs using pre-smart technology in Nairobi. We also worked with fascinating problems where it was detecting illegal chainsaw activity in rainforests using audio. And it both gave me this idea that machine learning is just so exciting and so interesting, but also I was working with people who were a lot better than me. And so I think that's also was fairly critical in just my own sense of measuring my technical progress and feeling like, wow, I really want to learn both the tools and the framework to be able to solve some of these problems. The second part really was I've spent 2 years working deploying algorithms. So I joined an online education company called Udemy, and there I was working on recommendation and spam detection. And that was fascinating because a lot of it was how do we deploy models, which is very different from only focusing on developing models, mainly because you're willing to give up quite a bit of accuracy in order to deploy successfully and have a robust deployment pipeline. So for me, kind of at the end of those two experiences, and Delta has really been in parallel this whole time, for me, brain was really a question of, do I enjoy research? Because I really enjoyed all these very domain-specific questions. Right. And I want to see, firstly, does that curiosity translate to a research framework? And is this satisfying in the same way? And the residency has been, in particular, in doing research at Brain, has been a very good way to answer that question. So that kind of brings me to today. A lot of what I've done over the last year has been doing research on interpretability and now model compression at Brain.
Have you arrived at an answer in terms of how you feel about research? And I'm curious, from the perspective of someone who is new to research from an applied background, and not to mention a self-taught background, like, how has that transition been for you? How's that experience been for you? What do you like about research? What do you prefer about application?
Yeah, that's an excellent question. And it's important because I think that there's few of my colleagues who have perhaps experienced both. And so my answer, although it's a sample size of one, may be useful in some ways for other people thinking about whether they want to do research or stay in applied. I think there's different pros and cons. So with my applied work, a lot of what is important about the skills and the thought process that applied work imparts is that you can't really abstract any part of the pipeline. So you have data preparation, and your data is normally very specific to your use case. And so often you spend a lot of time getting usable data. And many times, for example, in the Delta projects, the cost of incremental data collection is fairly high unless you're using a mobile app or something that automatically generates new data. So understanding the distribution of your data is much, much more important. And then you also have the deployment phase in applied, which again imposes very severe constraints on what you can actually do, because you need to justify every additional step of complexity that you add to a model. On the other hand, I think research is this very kind of particular way of having a discourse about a problem. And it's often prickly. And I mean that in the sense that you're often using a very clearly stated set of assumptions about how you want to navigate a given task. But you are advancing solutions that should have a contribution, even if at times marginal, to a large set of problems and not just a specific problem. But why I raised the difference earlier of you have to think about your data pipeline, you have to think about your deployment for applied, is that research, or at least the current body of machine learning research, largely abstracts those two. So we work with 3 data sets. And I'm sure most researchers listening know which ones, but MNIST, CIFAR, and ImageNet. And we take that as given. And we're not too concerned about deployment. We don't really think about, there's very interesting new research that is focusing on the interaction between the model and the hardware. But for the large part, we focus on the representation. And so a large part of our time is very much thinking about how can we learn better representations given this data, and not really fussing too much about the details of how it translates. This is good and bad. It really, and maybe here's, and probably I sense implied in your question is also, for me, how abrupt the transition was, and like what were challenges personally, and what did I enjoy. I think that doing this and doing the residency is a very particular form of entry in research, because you have a lot of contact with very senior established researchers in the field, probably even more so than you would have in a PhD program. So to a large degree, if anything, I would say the fact that I really enjoy research and the fact that I think this way of discourse is valuable is probably also because I've had a very exciting set of collaborations here. And a lot of what determines how you think about a problem is also who you work with. And so that has been like very charged and very exciting. I will say I do miss the feedback loop that comes from deploying a model, because a lot of how we measure progress on a task in research are perhaps metrics that might, and I say this with a note of hesitation in my voice because I think it's an active debate, but we use metrics like accuracy, or for interpretability, it's even more complex. What metrics do we even use? But these are metrics where you may actually have a very high, may have a successful representation that inches up interpretability, accuracy for these given data sets, but it's unclear, like if you were to actually translate that to real world tasks, like whether that would be as successful or not. And I think I'll pause there because I'm curious, like whether anything I said I should elaborate on. I threw a few things out there.
Well, what's interesting about what you said was that you're doing research at one of the places that, along the spectrum of pure and applied research is probably a lot closer to the applied side than most. And in fact, we see all the time how research that's happening at Google Brain ends up in products like Duplex and the Google Cloud products. I'm wondering how that fits into the equation. And I guess what's interesting is that you still characterize it as fairly disconnected from application, whereas I tend to think of it as fairly close. And I'm wondering if you can provide some context for that.
Yeah. So I think it's more to do with incentive structure. So brain is exciting for researchers because there's no incentive in how we, in our iteration cycle of ideas, that obliges us to think about product at all. In fact, like that's what's so charged about the atmosphere, is that we don't have to, at any time, even if we don't deploy to a Google product or to any product, our research can still be considered successful and a contribution. A larger part of how brain specifically is orientated is around contributing to the wider research discourse. So that's what I meant by it's removed, is that largely our framework is the same as academia, where we start with an idea, and then a lot of times the culmination of the idea is a successful contribution to a conference, or it's open sourcing code, so things that enrich the larger community. That being said, I will say one way in which perhaps this is a little bit different from what we imagine academia to be, is that because it's an industry lab, there's much more room to do empirical experiments, which I think is quite exciting. And when I say empirical experiments, what I mean is that oftentimes previously, I would say, there hasn't, you can kind of see the evolution in what data sets are considered the benchmark for justifying a certain hypothesis or justifying a certain theoretical approach. And we kind of moved from MNIST being sufficient to now probably most people would not consider MNIST sufficient as evidence for your hypothesis is correct. And now you have SciFar, and I would say at places like Google, these research labs, it is possible to do large-scale experiments with data sets like ImageNet and do a lot of empirical and important empirical work to corroborate hypotheses, or to, perhaps to say that certain hypotheses that were previously held may not be correct given the data. So that is exciting. And that's one way in which the conversation is different. That being said, I'm sure there's aspects to a cultured academic lab that foster new directions of thinking that perhaps because we can iterate so quickly with experiments here, we may not inform that in the way that we talk about these things. That I'm not sure about because this is the only lab I've known, but I can imagine that would be a counterpoint that someone would say.
It does surprise me a bit to hear that you are working day to day with the same data sets that everyone else is. I would have imagined that you had some super ImageNet++ or SciFar++ that you're using. And, when you're ready to publish, you dumb things down for the outside world.
I can only speak for my experience, my immediate colleagues, but there's no ImageNet++ that we just scurry around with behind the scenes. So, and perhaps that's because of essentially the cost of switching between data sets. So this is another interesting insight, is that a lot of the reason why this is my opinion, but I sense a lot of the reason why we're using these same data sets is that often doing an idea and implementing on these data sets, when you try and translate it to perhaps a more realistic data set or more complex, it's not that you would get different results, it's just that like the implementation and how you go about it may be fairly different. And so given limited time resources and given that everyone else is articulating progress in terms of these three data sets, if you're a researcher, you also want to be talking in the framework of these publicly available data sets. Because research is a lot about how do you measure progress on a task and how do you articulate convincingly that you've made a contribution. And that largely involves referencing prior work in the same area that has used these same data sets. And then you say, given that this is a commonly understood reference point, this is what I advance as further progress. That kind of restricts how much you can jump back and forth. But maybe some researchers are using ImageNet++, and I just haven't been kept in the loop.
In some ways, I'm thinking it's a bit of a negative critique on the state of our methods and research in general, and perhaps even application, that we're so tied to specific data sets. I certainly having a data set as kind of a lingua franca for comparing results and all that makes sense. But there's also a degree to which our methods and our research results are tied to these specific data sets, kind of the classic overfit on ImageNet. Do you see that as well in your work?
Yes, Sam, you're bringing up an important point, and this is one that I think is a very active thread of discussion at Brain. I sense I sense I've heard two different perspectives on this. There's a general consensus that, as you described, overfitting to the data sets that we have. And I would say that few researchers would dispute that entirely, or would at least acknowledge that we've really centered a lot of attention on these three data sets. You could even go further. Like both the fields that I've worked in, interpretability and model compression, a lot of the focus has been on computer vision. In fact, I would venture that very few papers have talked about different tasks or different architectures, even though there's an urgent need for interpretability beyond just computer vision models. And then I kind of said at the beginning, there's two perspectives to this. The other perspective is that research is a very particular way of talking about a problem. And it's the framework of how discussion occurs in research community is by design fairly narrow, mainly because it's a very precise way of advancing a scientific hypothesis and a contribution. So it's unclear to me that if someone did deviate from this norm and showed up with a new paper on a new data set and said this is a huge improvement, I think either they would have to benchmark previous methods on a new data set, which is a large technical contribution depending on the field, or I would be left with doubt as to what their contribution actually is. And so that kind of captures the dilemma that a lot of researchers feel, is that they acknowledge it, but it's unclear how to proceed.
So your particular research, or at least the research that you spent the most time on thus far, is around interpretability, and you're starting to do some model compression work now, but tell us specifically about the interpretability work that you've been publishing on.
Maybe I'll start by just introducing interpretability and how it's commonly thought of within research. And then that will provide some context for the work that I've been doing. Interpretability is a very interesting problem. It's interpretability broadly. When I ask, for example, Sam, if I asked you, do we want models to be interpretable, what would your answer be?
Do we want models to be interpretable? I think sometimes if it doesn't cost too much.
Excellent. Interesting. Yeah, you captured one of the key misconceptions that exists in the field, which is that all models must be interpretable. In fact, there's like nuances there, which is what you're describing. The starting point when I ask most people this question is that it's a firm yes. So I like that you hedged. And I think that's because we instinctively think of interpretability as this desirable property, kind of like fairness or bias. And it's interesting because then the next question is, well, what do you think is an interpretable model? And that's generally where there's uncertainty on the part of the person who's answering. Maybe here I'll say is that interpretability within research has really focused on this idea of, for these deep neural networks where we can't articulate in a compact way what the function that the model learned is, can we arrive at a methodology to try and explain the model prediction, or perhaps even the model function, which means the model function, can we understand how the model maps every input to every output? And you illustrated one of the key misconceptions is that the degree to which we want to do this and where we really want to invest effort may in fact depend upon the task. So you talked about the burden. Well, the burden can be thought of in a few different ways, but one way is this idea that for some tasks, like if we can't correctly explain how the model arrives at a decision, the cost on human welfare may be intolerable. Like examples of this could be, for example, healthcare, where we're using a deep neural network to arrive at a diagnosis, and then the doctor has to try and explain that diagnosis to a patient. And if there's an incorrect explanation that's given to the doctor, you can understand it has perhaps as a society, we wouldn't be willing to tolerate that. However, there may be other tasks where either because the actual cost to humans is seen to be, I hate to say the words low impact, but at least there's not significant notions of decreasing welfare involved, or the task has enough empirical evidence where we're just more confident in the overall behavior of the model. Those are tasks which are currently said we don't need to focus as much as interpretability because we have reassurance in different ways that this model is working the way it is. The other key challenge about interpretability is that it's very unclear when we've actually arrived. And this is really the tricky part, is that when do we say this model is interpretable? We're happy, we signed off, job done. In fact, it's both hard to measure progress on the task, but interesting enough, the finish line may look very different for different people. The burden we carry of delivering a satisfying, interpretable explanation may be different depending on even what our downstream task is. Like a good example of this is if you're sitting on a plane and your plane is just delayed, and the pilot comes on and says, "Oh, we have error with one of the engines on the plane. And then they say that we're fixing it. We have ground staff. So as a passenger, you're just, sitting in the cheap seats, and like you actually don't know much beyond there's some technical error that's being fixed. The pilot probably knows a lot more. They've probably been talking to the ground staff, and they have an understanding of at least like what part of the plane, what would it influence. And then the ground staff probably has the most technical level of conversation because they're precisely locating a certain sensor. And so when the ground staff tells the pilot that it's fixed, that probably involves some level of technical detail, so the pilot's confident. When the pilot tells the passengers, it's normally, okay, sold, we're taking off. And so I think that in a compact way kind of describes that we may need different levels of explanations, and that is okay. In fact, like if the pilot were to tell you every single technical detail of what the ground staff told them, we may feel slightly overwhelmed, or at least we would feel, oh, wow, this is really serious because they're telling a lot of different jargon that I don't know, and I'm feeling very, very disorientated. And a lot of interpretability is trying to understand how do we both create a meaningful explanation, and meaningful here really means given the domain and given who the person is and what they have to do with that information. But the topic of my research has been that it also should be reliable. And by reliable, I mean that in creating a meaningful explanation, we shouldn't communicate information that is not an accurate reflection of what the model has learned. And this is a delicate area because in some ways the key problem is that with deep neural networks, we don't know the ground truth to begin with. So it's hard to say this explanation is better than this one because we don't know the true explanation. And so a lot of what I've worked on for the last year is how do we create frameworks to measure progress on this task, even in spite of the fact that there's no ground truth.
In setting the stage for us, you pointed out the distinction between, I think you referred to it as interpreting model function versus model decision, but you also used the term interpretability and explainability interchangeably, or at least that was the impression that I got. I tend to think of like interpretability as that functional, what is really happening in the model, and explainability is, given the model is more or less black boxy, how do we make some sense of what it's telling us? Is there a distinction there for you at all, or do you use them interchangeably, but, in light of acknowledging the two different tasks?
Yeah, really what I meant when I talked about explanations is this idea that a lot of interpretability, so in interpretability research is often explanations is considered a subset. Explanations are just trying to explain a single example. So that's how I use that word there, is that for an explanation, you have a given input and you're trying to say, for this input, why did the model arrive at this prediction? Whereas when you're trying to understand the function as a whole, you're trying to understand perhaps what was most important to the function that the model learned over at least a larger subset of examples, if not the entire data set. Most interpretability work for deep neural networks is focused on the single example explanation. So there, often it's an image, and you're trying to say, why did the model arrive at this prediction for this image? That has been the largest part of the discourse so far within deep neural networks.
And so your work is almost at a meta level. It's there's a bunch of research that is happening and needs to happen in interpretability, but how do we compare these different results without really knowing what the model is doing in the first place?
Yeah, I love how you you captured that very succinctly. Yeah, that's exactly the challenge. We now have a rich set of methods, and the question that has to be answered is, okay, I have all these different methodologies for arriving at an explanation, which one do I use? And so my work is focused on methods that estimate feature importance in a network, and they estimate input feature importance. So the estimators that I have evaluated with my co-authors in both pieces of work that I did over the last year have asked, in this given input image, these estimators will say this pixel will essentially arrive at a ranking of these are the most important pixels for the model prediction. So imagine an image of an ostrich, and these estimators will arrive at a different estimate for how important the pixel of the ostrich nose is to the prediction of the model at the other end. And the first piece of work that I did was it essentially started with a premise that one definition of reliability is that if the model is not affected by a transformation of the input, then these estimators should not be affected. Because if the model is unchanged, we want these estimators to reflect the model. And to carry out this test, we established a very narrow ground truth, where we created a transformation to the input, which was a mean shift. And then by construction, we ensured that the model was not affected. And so the gradients of the model did not change. The weights of the model were unchanged. The model was impervious to this change in the input. But then we showed that many of these estimators changed.
What specifically do we mean by estimator here?
So estimators, I actually use interchangeably with methods. So think of it as just these set of methods. And I use them as estimators because I think it's useful to think of some of these tasks as trying to, because there's no ground truth, really that model is trying to estimate what's important. And we're just trying to evaluate whether that estimate was good or not, whether it was accurate or reliable.
When I think of the description you gave of the method, it calls to mind the LIME method of explainability, which also seeks to perturb or inject noise into the inputs and use that to determine, what parts of the input are most relevant. Can you maybe, for those that are familiar with LIME, talk about how the two ideas relate?
They relate. It's the same idea. Yeah.
Okay.
That was an excellent way to anchor the conversation. Yeah. So when I talk about methods or estimators, LIME is a key example of it's an example of an estimator that many people are familiar with. And other examples of methods or estimators can be things like just taking the gradient. So you end up with a gradient heat map, or it could be guided backprop. Or there's integrated gradients, which is another fantastic example of like an estimator that is trying to weigh importance of these input pixels. But yes, I'm really glad, Sam, that you interjected there because it's one and the same. So
LIME is one of these estimators, and it's doing noise injection, but it sounds like you're essentially taking that same approach, but applying it again at kind of this meta level to evaluate the estimators.
Well, maybe not quite.
Okay.
Not quite. So LIME is one of the estimators that could be evaluated, for example.
Mm-hmm.
And I think perhaps if you think about it, so we have something like LIME, we have these other methods that are estimating importance, and in both in my line of research, essentially what I'm asking is, are the estimates correct or not? Like LIME is very intuitive because I think it's exciting because it gives a clear explanation of what the model arrived at for that prediction. But the question I ask is that how do we actually know that what is exciting to us as humans is also a reliable reflection of the model? And to do that, the first piece of research I described essentially takes these methods and says, we've applied a transformation to the input images, which is a mean shift, and the model's not changed, do the rankings change? And if they change, then that's not that is considered a failure in this test case, because they should simply reflect what the model thinks is important. And if they diverge from that, then it's unreliable. The second research that I did was one step further, and again, this idea of how do we measure progress on this task of reliably estimating importance. And what we did there was we said, okay, these different methods all rank the pixels. Let's remove the pixels that they rank as most important, a fraction, and let's then give those examples, these modified inputs, back to the model. And the presumption is that if the methods actually identified what was important, if they accurately rank these pixels, then it should really damage the model if you're training it again. And we compared it to a random removal of pixels. So really we're asking, if you randomly remove pixels, essentially you're randomly assigning importance to the inputs. And if these methods don't damage the model more than just a random removal, then in some ways they're less able to accurately rank than just random removal. So that was a very interesting piece of research. And it's kind of again at this idea that in the absence of any ground truth, what we need to do in this field is kind of state precisely these desirable properties and articulate frameworks in which to measure these, because then at least we have an established, we've articulated a way of saying we are measuring it in this sense, and given this framework, this method appears to be more accurate or reliable.
And so was the end result of these two research efforts a kind of a ranking of these different estimators? And if so, what did you tend to find? But also, is ranking these estimators a one-dimensional thing? Or are there multiple ways that we should be comparing these different methods?
Yeah, you raised an important point. So to kind of share the results, on both we found very interesting results. And in fact, kind of advance, at least for me, I felt taught me new things about how the model actually arrives at feature importance. So in both, it was a little bit of a grumpy picture. I'll put it delicately. We found that in the most recent work, which is a paper called Remove and Retrain, where you're essentially removing the most important and retraining the model, we found that the estimators that we considered, and we only considered a small subset, so I'll caveat with that, they didn't perform better than a random assignment of importance. But we did find this, which is fascinating, which is that if you ensemble, so if you take for the same image, you take various noisy estimates, which means that you add noise to the estimate and then do that repeatedly, and you combine with squaring. So these are two separate transformations applied to the estimate. So imagine this for Lyme, like essentially you'd be taking noisy Lyme estimates, squaring. We found that far outperformed a random estimate of importance. And so that's kind of interesting aha moment, because it's not quite a aha moment because there's not the theoretical justification yet for why that is the case. But it suggests, firstly, the importance of empirical research, which is an option you discover odd, interesting things that motivate research in a new direction, but also tells us that we, in some ways, how we're considering these estimators now, there's very exciting things that we can do that will improve progress on a task. And then you asked, your second question is critical, because you said, is this one dimension? Absolutely. This work should be considered one dimension. And in fact, like there's almost, even if we were to narrow it to reliability and accuracy, which is really what this work is trying to get at, there could be other dimensions for measuring this, because essentially what we've done is we've just stated this is our way of technically defining these properties, and given our definition, this is what we think are the best methods. Someone else would come along and say there's another way to define technical reliability, and given this, this is what we find. That's the nature of this field. And I would encourage that. I think it's important for researchers and for the community as a whole to think about how do we measure, how do we ensure that we are actually delivering an explanation that people can trust, that is a reflection of the model. I will say one more thought on that, and then I'll pause, which is that you can also think about a whole other set of desirable properties that are on the being meaningful to humans side. So often how that's measured now in the body of research is that user studies are conducted, and things like, do you trust this, are asked. And that in itself, I sense, could also benefit from a more, both larger scale treatments, but also much more nuanced, like, is for this task, for this person, does this make sense? Because inevitably interpretability is going to evolve on a few different levels, like based on our perception as a society of what do we need for us to trust technical implementations of deep neural networks, as well as in a job specific way, which is that, a doctor is probably going to always want an explanation of every example. It's always going to be at the single example level. But as a researcher, for example, what's more important to me, I would suggest, as an interpretability tool, is that I want to get a sense of the distribution, and I want to understand out of the distribution of data what data points are perhaps more either problematic, and you can define problematic in a few ways. But if I have a better way to understand what is different in a data set, that's helpful for me in understanding, am I comfortable to deploy this model? So all these vantage points will require different desirable properties. But I'll stop there.
One question that I did have was in the evaluating feature importance estimates paper, you look at, as you mentioned, a subset of these different estimator types, gradient heat map, integrated gradients, and some others. Is LIME a subset of one of these? Like, are you using a generic term of these that you include that LIME falls under, or did you just not look at LIME particularly?
We did not look at LIME, and I would be really excited to see the results on LIME. The constraint on these papers is always this tension between we have limited time and a certain amount of computational resources. But partly, I think what this motivates more than anything is open sourcing code, which is something we're doing for this paper. And that's important because really, if this is going to be a sustainable benchmark, researchers have to be able to self-serve and also be able to take what we did and apply it to their method. But I would be really interested to see the results of this for LIME, mainly because LIME imposes contiguous feature importance. By that, I mean that, let me frame this using a counterexample. So gradient heat maps, for example, don't require that feature importance a connected set of pixels. You just take the gradient of the pre-softmax activation for the model prediction with respect to the input, and then you rank. But that tends to result in very diffuse attribution, meaning that importance, when you rank it, doesn't concentrate exclusively on a set of connected pixels. Whereas LIME imposes this constraint by its methodology that importance is restricted to the connected pixels. Humans tend to, and I say this hesitantly because this is not a research conclusion, this is a hypothesis, but I sense humans tend to like connected pixels as more what they perceive to be interpretable. And so I would be excited to at least benchmark LIME or another example of a method that does assess feature importance in this way using remove and retrain, because it may have very different results, or at least tell us something about how connected importance versus this diffuse importance actually is related to the reliability of the method.
Interesting. It strikes me that when you know, from that perspective, the idea that humans prefer these connected areas versus diffuse areas almost says that humans want explainability that makes sense to them more than interpretability that might be more functionally accurate.
Yeah, I hesitate to say
because we're just talking here, isn't it?
Yeah, we're just throwing stuff out there. But I will, I will say the most how researchers articulate this in papers is quite funny. So this comes up. No one quite gets at this explicitly because again, it's not something that's exactly testable. And even in my current research, I don't benchmark any of these connective methods. So I really hesitate to venture. But what I will talk about this frustration with diffuse methods, because that's kind of a coherent pattern in these papers. Researchers will say that the method is perceived to be visually noisy. And that's seen as that's interesting, right? Because that actually says nothing about whether the method is accurate or not for gradients. It just speaks to our reluctance to either it's hard to discern what the explanation is saying, what's actually important in this image according to gradients. And that might be because as humans, we may not know what to do with the complexity. Again, here I'm using another word that is very subjective, like visual noise, the complexity of the explanation. Whereas if something is connected and placed in a specific area, at least it may be, I sense it may be more reassuring. But again, I think we're both throwing things out there. And that's what makes this domain so challenging, is that a lot of it is subjective. A lot of it is inherently like, my preference may differ, in fact, from your preference. And that's why there's no clear finish line.
And did you find that the specific approach to ensembling, you mentioned squaring the estimate? I'm not sure. Well, you can elaborate on that. But the question is, did it apply equally to all of the methods you looked at? Gradient, heat map, integrated gradients, smooth gradient, squared gradient, et cetera? Or are there specific formulas or formulations that apply to individual methods?
Well, this is the cool thing, is that it benefited all the estimators, all the methods that we considered. And I apologize I keep on interchangeably using those words. But but yeah, it really dramatically, I would say, improved the accuracy of the three estimators that we considered. And when I say it, like, it was firstly adding noise to the images. So for a single image, you would create a set of 15 noisy images, and then you would arrive at 15 different predictions. And given those 15 different predictions, you would take the estimate for the methods you're considering, you would square it, and then you would average those. So you're left with one estimate at the end again from these 15 different images.
And again, an estimate in this case is
LIME, for example.
But the actual estimate is a per pixel probability, for example, or it's something on a per pixel basis, right?
It's on a per pixel basis. Mm-hmm. It's often, in the case of gradients, it's not capped at a certain, it's just the magnitude conveys the importance, so it's not a probability. Okay. But other methods will cap it so it's cumulative. So the sum of all the estimates of importance should sum to one. That's a property called completeness. But yes, so you're correct. It's on a per pixel level. So you're averaging across however many noisy estimates you have to arrive at a single estimate for a given pixel.
So that's your interpretability research. If you have a few more minutes, I'm curious about some of the model compression work that you're doing. And that ties into the event that's kind of brought us together, which is the Deep Learning Indaba, which is coming up in South Africa. And we're well beyond our typical background segment here, but
Yeah.
you grew up in.
I had that similar reaction when you said that. I'm like, oh wow, this is introducing some context late in the game. um, but it's yeah, I grew up in Africa, in mostly in Southern Africa. So I grew up in Mozambique, South Africa, Lesotho, Swaziland, Kenya. My family just moved to West Africa. They just moved to Monrovia, Liberia. So the Indaba's coming up, you mentioned, but also Google is opening this AI lab in Accra. And both are very exciting because so much of it, I think, is quite exciting personally for me, as a way to, well, Indaba, I would say, is very much directly doing this. Indaba, the motivation is let's build technical capacity, and that's the most important determinant. I kind of mentioned this when I talked about what made this year possible. It's contact with very experienced researchers and just the ability to collaborate. And I think the Indaba is really in the same vein. Like, you're bringing these researchers from all over the world and all these students and also practitioners from all over Africa to the same place. And wow, is that exciting. I don't need to be too exuberant about it, but I think I recently went to Data Science Africa in Kenya, and the energy level is insane, mainly because we, right now, like, technical talent, I would say, is very correlated with geographic location. So places like San Francisco, New York, Paris, a handful of other geographies have a lot of I would say, experience. And as soon as you leave one of these cities, you realize it's a cliffhanger. Like, the ability to have a community to learn and grow in the places where I grew up is extremely limited. And so for students who attend these gatherings, it's just really, they're so excited because this is a way for them to connect. Many times what they've been studying by themselves online with people who are actually doing this and practicing in the field or doing research. So that's why it's so exciting. I forget the second part of your question, but maybe, maybe I'll pause there.
Well, that provides some interesting context for your move to the Accra office and your work in model compression. I think that was the tie-in that I wanted you to elaborate on.
We threw a few things in there. Well, the Accra office, so Moustapha Cisse is leading the Google AI Accra office, and he's amazing. He's one of my both mentors and collaborators here at Brain. And the Google Accra office is like any other Brain office. So the goal is to go and attract the best researchers and do research. So I'm very much in the same vein of a lot of the things I've described today. I think what Moustapha, I sense, would agree with is that there's this other idea is that by placing researchers in different geographies and in different environments, you have often very novel approaches to ideas. And that is both because the resource constraints that you find may be different, as well as because simply, like, a lot of researchers who you work with and like your day-to-day conversations, and you may find novel directions because of that. The other hope for this Accra office is that having researchers there may provide important externalities for the ecosystem as a whole. And Moustapha has also really championed this master's program, which will is also starting this year, and that's supported by Facebook and Google, I believe. But how that relates to model compression, it doesn't necessarily have to, but it happens to for my current research, which is also with Moustapha and Eric and another collaborator, Trevor at Brain. There, what I'm interested in is this idea that really the starting point for this research is, why do we need such large models? Deep neural networks are notorious for the amount of parameters that needed, and also the tendency for the number of parameters to grow year over year in the body of research. But I think it's interesting if we impose different constraints. Like, for example, if we actually think about deployment in very resource-constrained environments, such as mobile phones, which a lot of parts of Africa have jumped directly from neither having a laptop or a mobile phone to just jumping to a mobile phone. So if we think about that imposes very different resource boundaries than what we're currently used to. And often, like, thinking about that drives interesting ways of attacking the same problem. There's a great example of this in how engineers at Google, and I believe also at Facebook, have tackled how do they make engineering products which are better suited to low bandwidth or limited connectivity environments. And the solution was, one of the solutions that we experience and is highly visible is this idea that there's an entirely separate internet connection that you can connect to that will give you the experience of being in a impaired bandwidth environment. And this was actually like a startling catalyst for a lot of engineering innovation around these problems. Again, like this is my interest in model compression, I sense could have been equally pursued in Mountain View at Google Brain headquarters or in the new office in Accra. But it's exciting to, in a sense, like energize like what I'm thinking about by also connecting with people who are experiencing the pains of trying to deploy models. And that's one of the most frequent questions that you get from students when you go teach in a place like Nairobi, is that a lot of people have an idea, have tried to implement it, and now are trying to deploy it using something like TF Lite and are experiencing severe pain points. That's exciting for me, at least. My research direction is specifically on this question of how do we effectively remove weights from a model while preserving accuracy. But there's a few different threads to how people tackle this problem. You may have to rein me in again if we get started. So I'll pause. I don't know if there were any immediate questions that.
It sounds like from our earlier chat that you can't go into a ton of detail about your research because it hasn't been published yet. But if you could give us an overview of kind of the landscape that you're playing in as we wrap up, that would be great.
I'll mention probably 4 key directions that this problem has been thought about. And the other defining characteristic of this field of research is that I sense it's being underserved. There's been very little attention. It's a rather new field of research. But some of the solutions are actually very old. I know that was like an odd caveat, but I'll give you more context for what I mean. So there's the key approaches to this problem are that you have things like pruning, and pruning says, let's reduce the number of weights in a network. And you either do that over the course of training by setting certain weights to 0 or regularizing so certain weights become very close to 0, or at the end of training by saying, this is our model, and now we're going to try and arrive at a much smaller model. And then the metric that's being optimized for is normally a level of sparsity, given a certain degree of accuracy. The second approach, which has been enormously successful and in some ways has taught us a lot about deep neural networks in general is quantization. Quantization refers to this idea of you have a certain level of precision in the weights themselves, and you can essentially take a floating point weight and you can reduce the number of bits, and then you can still have a remarkable level of accuracy. So this takes like most often a trained model, and then changes the representation of the weights. And this has huge implications for memory. So often you're able to really improve memory of the models, the memory needed to store the models, by simply changing how the weights are represented. There's this third direction, which is model distillation. So this is also interesting enough present as an interpretability direction, but you have this teacher model, which is your massive deep neural network, and then you're trying to train a student network to have the same accuracy as the teacher network with a fewer amount of parameters. And all these are quite exciting. The fourth, which I think is probably the most underserved, is this idea of like trying to do things that are optimized for the actual hardware. And this is tricky because, this is a nice loop back to how we began this conversation, but it's hard pursuing research that is optimized to hardware because hardware tends to be non-standard. And so think about a TPU, which is made by Google as one of their first hardware that's directly has in mind deep learning, and then a GPU made by NVIDIA. But even when you think about cell phones, it's non-standard. And so this research, in some ways, the constraint is that you want to make it generalizable enough, but you still want to make significant inroads into how it's being deployed. But I started this kind of framework by saying this odd disconnect. I said, in some ways this is a very new field of research, in other ways it's not. I'm thinking specifically of pruning. So pruning has actually been around since the 1990s. So pruning was the first field I mentioned where you're trying to remove weights and arrive at a smaller model. And there was the first paper came out in the 1990s. It was initially called double backprop, but LeCun proposed it in the form of optimal brain damage, which I think is a great name for a paper. It certainly has a ring to it, but he proposed one of the first methods. And so some of these approaches have been around for a while. It's just that there's a new level of attention, both because there's a sense that now the resource constraint is firm. There's a lot of discussion around Moore's law and how we can't quite get the hardware to just catch up with whatever researchers want to do. And then instead we must think of like interesting ways for researchers to meet the hardware. And that's not an easy feat because hardware and research has tended to be very siloed in both directions. So that's what makes this particularly perhaps a very interesting time for a lot of the enthusiasm around this subfield.
I think we could launch into another hour-long conversation about this topic.
I did warn you would have to rein me in, so.
But we will have to find a time and place to reconvene on that one. But Sara, thank you so much for taking the time to chat with us. It's been a pleasure to have you on the show and to learn about what you're doing, across all the various things that you're working on.
Thank you so much. It was really fun chatting with you, Sam. I think Sam had mentioned offline, which I'll repeat here for social peer pressure, but he mentioned that he would come visit the Ghana Accra office. So I plan to hold you to that.
Let's do it for sure. And you mentioned earlier Moustapha Cisse, who is heading up that office. For folks who didn't catch it, I interviewed him when he was at Facebook AI Research, and we will drop a link to that show in the show notes. But once again, Sara, thanks so much.
Yeah, thank you.
All right, everyone, that's our show for today. For more information on Sara or any of the topics covered in this show, visit twimlai.com/talk/189. To follow the entire Deep Learning Indaba podcast series, visit twimlai.com/indaba2018. Thanks again to Google for their sponsorship of this series. Be sure to check out the 2019 AI Residency program at g.co/AI Residency. As always, thanks so much for listening, and catch you next time.